Okay, should we start? Very well. So what is the goal of this lecture? Okay, so in this lecture I will try to give you some of the ideas and some of the details for producing continuous solutions. So let's say the overall goal will be the following theorem. Okay, let me abbreviate La'szlo's name as S. So this was in 2020, in 2012. Okay, so what we want to prove is the following. So there exists continuous solutions VP on the periodic three-dimensional torus times 0, 1 of the Euler equations. For which the total kinetic energy is not constant. Okay, so I will call the total kinetic energy E of t. And this is just the integral, so 1/2 of the integral over the periodic torus of the modulus square of the velocity. So this one is not constant. Okay, that is what we will try to do. And I am following two references. So the one is the official reference, the official paper, the first time that we proved this, which is called, so the name of the paper is called Dissipative Continuous Euler Flows. And okay, I only wanted you to discover this a little bit later, but now you would legitimately ask this question: why are you saying dissipative? The reason is that what we will really prove is the following statement. You give me this function over here, satisfying certain mild regularity assumptions and positive, say C1, for instance. And I will produce a pair which solves this and which has exactly that function. So in particular, if you choose that function to be strictly decreasing and say sufficiently regular and positive, you will have a dissipative, what we call the dissipative continuous Euler flow. Okay? So, and then I'm not only using that, I'm also using a survey article that we wrote for the Bulletin of the American Mathematical Society. It's one of the two. It's the second one. So this reference is called High Dimensionality and H principle in PDE. Okay, and just for reference, Some other people call the H principle something which is due to Boltzmann in physics, and it's a completely different story from this H principle, which is due to Gromov and is in geometry. On the other hand, if I write it down, the H principle of Gromov is with a little h, and the H principle of Boltzmann is with a big H. Okay? So when I write it, there's no confusion. Okay, very well. So how do I want to actually prove that theorem? So to prove that theorem, again, like in the last two lectures, I want to set up an iteration, okay? I want to set up an iteration, and so I want to understand what type of kind of perturbation of the Euler equation I want to write down, okay? So that I will have a sequence of solutions to a system which is not exactly the Euler equation, is the Euler equation plus some error term, and the goal will be actually to get that error term going to 0, okay? So we call this system, and you probably saw it in the other lecture, Euler-Reynolds system. And it's justified, I mean, the name is justified by the fact that indeed it exists in the literature in classical fluid dynamics, where there's something which is called the Reynolds stress, which in some sense is measuring how far a certain object is from being a solution of the Euler equation. So if you remember in the second lecture, so we wrote the Euler equation in the following way. Okay? We wrote the Euler equation in the following way, and then we found solutions. Oops, something missing, sorry. And then what we did is we found solutions of this linear PDE, for which instead of having the equality over here, we had a strict inequality. And then we were improving U and V in such a way that this strict inequality became kind of closer and closer to be inequality, okay? So given that intuition, it stands to reason that we might take this guy over here, give it a name, let's say R circle, and say that that one is the error that we do in solving the Euler equation, okay? But now if you introduce, right, let me call it minus R circle. Now, if you introduce this variable and you put actually the definition of U back in here, you just find, you know, you can eliminate U back, and what you find is the following system. The reason why I put actually a circle over there is to remember the following fact. That guy, that R circle, is trace-free. The typical Reynolds stress is actually it's not trace-free. Oh, I forgot the pressure. Okay, the reason, so let me just make one remark. I can make this tensor non-trace-free. I can add a function times the identity at the price of simply changing the pressure over here, okay? Because the divergence of something times the identity is exactly the gradient of that something. So in that sense, it stands to reason that I want to consider here things which are kind of trace-free. Okay, so if I put R circle plus some function f times the identity, and say P, so if I make this transformation, so I map R circle into R circle plus a function times the identity, and P to P plus the function F, I'm still a solution. And I want to remember even another thing very much. So this will play a fundamental role. If actually the function f is purely a function of time, I don't even need to actually add anything to the pressure, right? I mean, because there is a divergence over here. So I'm not really seeing that derivative. It's a pure function of time. So now I want you to remember that, because this is, at a certain point, you will recognize this is one of the reasons why in our proof, we will be able to actually prescribe this energy, E of t. It will play a key role at a certain point. Okay, so here we go. The goal then is the following. So produce, so the goal is somehow going to be the following. So fix some E of t. Nice. So positive everywhere, sufficiently smooth. Okay. Produce a sequence let me call it VQ, PQ, R circle Q, okay? Solving the Euler-Reynolds system. And having the following properties. Okay, so first of all, I want this sequence to converge in C0, VQ, PQ. And the way we will do it, and this should not come as a surprise since of last lecture, the way we will do it is to get an estimate between the C0 norm of the difference of two consecutive functions and hope that I get actually a summable series, so that my sequence is actually Cauchy in C0. So let me write it over here directly. So I will have VQ plus 1 minus VQ in C0 plus, okay, plus, say, PQ plus 1 minus PQ in C0, which is converging. And at the same time, so this will be the first condition. Then I will have another condition, and of course it's what you all would be expecting. So this R circle Q in C0, I want it to converge to 0, so that the limit it disappears. And that means that the limit of this sequence, which now is a sequence which is converging in C0, is going to be an actual solution of the Euler equation. And then I want, of course, kind of E minus the integral 1/2 the integral of VQ squared of x dx. So I want this one also to converge to 0 in C0. And let me stress, this is some function E of t that you have actually fixed yourself in a sufficiently nice class. And so you fix it to be something which is non-constant, and you have the theorem as it's written over there, or you fix it to be some function which is decreasing, and then you have the dissipative continuous solutions of the title. Okay, that's what we want to do. Okay, and let me start with the first remark. So you've seen already a few times these anti-divergence operators, okay? So there's a basic fact. So there are two important points. So important starting points. So given some reasonable function f, I can find a vector field whose divergence is that function. And given some reasonable vector field v, I can find a symmetric traceless free tensor R whose divergence is that vector field. Now, what do we mean by reasonability? Well, if on the torus something is the divergence of something else, the integral over the whole torus of that something has to be equal to 0, simply because I write integral of the divergence and then I integrate by parts, okay? And that's actually all you have to do. So if you want, so you have a proposition. So there exists a nice operator, and we will see what we mean by nice. So it's an operator that has certain estimates, which inverts the divergence. Now, the divergence inverts in one of the two, so what is it? A right inverse or a left inverse? A right inverse, I believe, right? So we're actually finding a right inverse of the divergence, not a left inverse. So, and there is not even a unique right, I mean, there is not a unique way of inverting it, right? So because there's plenty of divergence-free vector fields. So you find something whose divergence has the correct quantity, I can add a divergence-free vector field, is still another something. So if you're looking for a nice way of inverting it, it means you are looking for a nice way of selecting one solution in such a way that it depends somewhat in a continuous way compared to the data that you're given, okay? So this is what we're going to show. Somehow there's a nice operator, divergence to the -1, on the space of smooth functions and smooth vector fields with average 0. Okay? So actually, let me call one guy, so people like it to call it divergence to the -1. I actually like it to introduce this operator R, which looks like I want to compute this R circle. That's exactly the idea somehow. So rather than like looking at system as the system in 3 unknowns, I'm really thinking about the following. So I solve for the divergence-free equation in V. That I do. So I'm looking at the divergence-free vector field. And then I'm looking at a scalar function, which is going to be my pressure. Then I compute this left-hand side, and then I use my operator to get this one guy whose divergence is equal to that. And notice that I will need to only take care of one thing. This is going to be divergence-free, this is going to be divergence-free. It's actually important that this guy is divergence-free too, because otherwise I cannot invert the operator, okay? I cannot invert the divergence. So therefore, the goal is rather, the goal is somewhat something like this. You are given a tripole VQ, PQ, and R circle Q with certain properties. I am trying to add a perturbation, which is going to make this side, so VQ plus 1 and PQ plus 1, much closer to the being a solution of Euler. So which means in some sense that the perturbation that I'm actually adding, when I put it inside the equation, is going to cancel the error that I had on the previous iteration. A little bit like we did in the construction for the C1 isometric embedding. So I'm iteratively trying to cancel actually the previous error. And then I will not be able to exactly get a solution. So I get my candidate VQ plus 1 and PQ plus 1, I plug it into the equation, and I solve for RQ plus 1, and then I try to get estimates on this RQ plus 1 and to show that it's actually much smaller than it was, than RQ was, okay? So, very well. What are these operators? So they are explicit, the ones that we will use. So you've seen that, then in the literature, you can construct these right inverses depending on what is your need, right? I mean, you saw that Vikram wanted actually something which was, doing something else. And you will see that there are many ways. And the reason that there are many ways is because I have this huge gauge of divergence-free fields or tensors, which I can use to my advantage. So if the solution that I actually find is not good enough, by using that operators, you might actually think of simply finding the correct divergence-free guys, which are going to correct it to something that it's better tailored for your problem. But, by and large, these operators that I'm going to show you, they are actually pretty good. And the reason why they are pretty good is because they, in fact, minimize something you will realize. I mean, it's something that you can try to do by exercise. They essentially minimize the L2 norm of the R circle that you're getting over there, right? I mean, that is a smart way of, for instance, getting a unique candidate for something which is not unique, right? So it's certainly a linear space. So you can minimize something like convex, like for instance, the L2 norm or the square of the L2 norm, and then you've got a unique guy, okay? And that guy has a lot of chance of being actually nicely behaved because you have a variational principle for it. But okay, this is the digression. So here are the operators. So how am I actually going to define divergence to the -1? Okay, that's pretty easy. So solve. So of a function f. So solve Laplacian of v, of phi equal f, and set v, so the divergence to the minus 1 of f, to be equal to v, to be equal to gradient of phi, okay? And so now there's a unique solution of Laplacian of phi equal f, but you are on the torus, so there is a unique solution if the average is equal to 0, okay? And you find your guy. Very well, so you can introduce an operator which I'm going to call P, and this is an operator on general vector fields. So P of V is going to be equal to V minus, and now you take divergence to the -1 of divergence of V. Now here you see this one is a right inverse, not a left inverse. So divergence to the -1 times the divergence doesn't cancel at all, okay? So you have a V, and now what I'm doing is I'm finding some canonical vector field whose divergence is exactly equal to the divergence of V. And then I subtract it. And so now this guy is divergence free. And it has a name that is called Le Ray projector on divergence-free vector fields of your vector field V. And the reason for that is because it's really the projection with using as projection the L2 norm of that vector field V on the space of divergence-free vector fields, okay? So the difference between the two is a gradient, is the gradient of that solution phi, and it's actually kind of the orthogonal segment which from V goes to your subspace in which you're interested, okay? So this is the Le Ray projector. Sorry? Yes, of course. I mean, like, okay, your projection, like, okay, you are in a Hilbert space, you have a closed subspace. What is your projector? Well, your projector is the element in your subspace which is closest in L2 norm to the guy, okay? For instance, yes, exactly. Very well, so how is my operator R actually defined? So I'm just going to give you the algebra, and you do as an exercise that it does the job. Where is it? Yes, here it is. Okay, so R of V is 1/4 the gradient of the Lyrae projector of U. Well, the derivative really, right? So this is a, of V. So this is really a derivative, right? So maybe I could call it this way. Because this is a vector field, this is a matrix. Okay, then plus its transpose. Plus 3/4. No, sorry. I really have to put U, sorry. Okay, plus 3/4 the derivative of U plus the derivative of U transpose minus 1/2 the divergence of U times the identity, where U is the unique solution of Laplacian of U equal to the function V. Okay? So this operator does the job. And of course, you recognize immediately it's only well defined if the average of V is equal to 0, because otherwise I can't actually invert the Laplacian. But I could extend the operator to general vector fields easily by just saying, let me subtract the average of V, and then I have something which is average free, and then the operator is always defined, but then it's not an inverse of the divergence unless the average of V is equal to 0. So what is really happening is that if I apply that operator, I get a symmetric tensor. The fact that the tensor is symmetric is pretty obvious by my writing, right? Trace-free, and that is not obvious, you have to make some computations, with the property that when I actually take the divergence of that RV, I'm going to find V minus its average. What you really should do is you should take the divergence of this RV and realize that it's actually going to be the Laplacian of U. And so then you get V minus the average of V. Okay, so that's the computation that you have to do. Okay, so there's going to be a lot of computations that we do with these operators. So something which is very annoying is the following. You gain one derivative, right? So like, you know, you're given a function f, and now you found something whose divergence is equal to that. So you expect actually your solution to be one derivative better than the other guy, right? And with some estimates, like, you know, if the function has a certain size, you expect the derivative of your solution to have a certain size. That is correct because you're solving an elliptic equation and then you're taking its gradient. So everything is correct, but not literally. So if I give you a continuous function and I actually apply this jazz over here, I don't get a C1 function as an answer. Because the borderline spaces actually behave badly. But as long as we stay away from continuous and C1, but for instance, we work in the Hölder category, and as long as we stay away from L infinity or L1, but we work in the LP category, then the operator really gains like one full derivative, okay? You have the Schauder estimates and you have the so-called Calderon-Zygmunt estimates. So it is a little bit annoying because we actually want to run our iteration scheme on the space of continuous functions, and we don't have good estimates for this guy on the space of continuous function. Does it change if we try to run our scheme in the space of Hölder functions? Not really. We still run into some of the same troubles anyway. So I will kind of ignore all of these troubles. I would sort of treat all these operators as if actually they have good estimates, even on the spaces where they don't have good estimates. So this will actually create some additional technical problems. And for instance, one of the technicalities that one has to face is that we will not be able, as in the Nash iteration for C1 isometric embeddings, to make these guys go like a power, okay, geometrically. We will actually, or like an exponential. We will actually need in the actual proof to go like a double exponential. But a double exponential with the second basis, which is very close to 1, so which is very close to an exponential. So I will just completely ignore those details. And when we are going to discuss about estimates and we want to kind of upgrade our construction from C0 to C alpha, we will treat it with the same kind of back of the envelope computations that we saw in the last lecture, as if I could actually run an algorithm which is going to kind of have an exponential ansatz. But that's not possible, and one of the reasons why it's not possible is certainly because I don't have the desired estimate for these inverses, okay? So that's one point, but now let me come to the important points. So the most important, like kind of the, well, let's say it's always kind of, there's always a certain degree of caution when you're actually ending up into philosophy or, aesthetic evaluation or merit-based evaluation, but it's probably the most important point. Okay, so let's plug in a very simple case of function f into this guy. And the same is going to be true for this operator R, only the algebra is more complicated. So rather than doing the algebra, I encourage you actually to do the algebra yourself. Okay, so let me take a function f of x of the following type. Something like a of x, okay? And then here I have e to the I, and then lambda, some direction k dot x, okay? And lambda, okay, so k is an integer vector, so that if I don't have the lambda, I find actually a periodic function on the torus. And lambda is a large integer number, okay? Although the fact that I actually have to choose lambda integer at a certain point, I will be swept under the rug. I mean, it will be possible up to like, making a little change on the lambdas that I have. Okay, and so now what happens if I apply divergence to the -1 over there? Okay, so if I didn't have this guy, I would have to solve the Laplace equation for that guy, which has a very explicit solution, right? It's like 1 over lambda squared modulus of k squared e to the I lambda k dot x. Okay, so if a is constant, so this guy is going to be, because then I have to take the gradient. So it's going to be, if my computation is correct, something like I k divided by lambda modulus of k squared, and maybe there's a minus, e to the I lambda k dot x. And then there's the a, right? Okay, that is if a is a constant. And you see immediately something that we actually like. If lambda is large, this one is very small, okay? What is happening if A is slowly varying compared to this fast exponential, right? Certainly this formula is not true anymore. But how far are we actually from having this ansatz, okay? So let us simply say that we guess that our divergence to the -1 is given by this f. We compute the divergence and we see how far we are from our target, okay? So if A is not constant, so if A is not constant, then the divergence of this vector field, let me call it something. Let me call it Z. So then the divergence of Z, okay, is one part that we like, which is when we hit with this guy, right? When we hit with this guy, we get we get the product of this vector with the gradient of this guy. So I multiplies I gives a -1. This becomes a plus. K times lambda multiplies scalar k times lambda, and it gives me lambda times modulus of k squared, which eliminates that. So that I like, right? So it gives me A, e to the I lambda k dot x. Okay, but then there's a remainder, right? And what is the remainder? So the remainder is something like minus gradient A divided by lambda, right? Dot ik divided by modulus of k squared e to the I lambda k dot x, okay? It has actually the same structure as the vector field we start with. And in principle, we could apply the same ansatz to this guy and get a correction to this, but the correction will have 1 over lambda squared, okay? And then I can keep expanding. It kind of stands to reason, and you can make a proof of it, that, you know, whatever I have over here is actually going to be kind of a smaller contribution than what I want, or what I have over there. So one silly thing that one could do is apply divergence to the -1 to this guy. If I have C0 estimates, the kind of thing that I have over there is actually something which is dominated by a constant over lambda, okay? So this tells me that it's still true that when I invert divergence to the -f to something which is of this form, I get an estimate which tells me that the size of the guy is 1 over lambda. But I want to argue better. I want actually to say that not only the size is 1 over lambda, but the principal part is this. So I apply this ansatz 1 second time, and now I have an expansion of this one plus something which goes like lambda squared plus an error, and the error will have the lambda squared. And now I invert the divergence to the -1 operator, and if I invert the divergence to the -1 operator, I get, because that one has size lambda squared, by the estimates for the operator, that the error that I do is also constant divided by lambda squared. So if I do it actually twice, I've discovered that divergence to the -1 of f is really this guy plus big O of 1 over lambda squared. And you can actually go with the Taylor expansion. So you can expand it how many times you want, and you will have some theorem which is telling you that the divergence to the -1 of f is equal to, like, you know, all of this expansion, and then there's going to be an error which is of higher order than what you actually left in the last term of the expansion. It's a legitimate Taylor expansion on lambda. With some warning. So this big O depends on higher derivatives of A, right? I mean, like, for instance, if I start doing like the first step, it depends on the gradient of A. If I do actually 2 steps, then it will depend on the second derivative of A, and so on and so forth, okay? And at a certain point, when we are going to discuss kind of C0 alpha, C alpha convergence, what will happen is that, well, what kind of a term I have over there, what kind of gradient is going to actually play a role, right? I mean, if it is the gradient or the second derivative or whatever it is. Yes, if you want, of course, to be precise, it will depend on the frequencies in which A is running with lambda. So what I'm going to show you is more kind of the baby version of a lot of things that Hyunju and Vikram and possibly even La'szlo already did last week, okay? Then you can, of course, build on that. If you kind of explore what are the basic ideas that you're using, you realize, okay, I was simply treating A as a very smooth function and then shooting lambda to infinity, but I can be quantitative, okay? So what I really need is that the frequency at which A is varying is somewhat sufficiently small compared to the frequency lambda that I'm using over there. And then you can start to be quantitative and do fancier stuff. But at this moment, I just want to actually get the qualitative picture. And the qualitative picture is that if you fix A and you give me the choice of like getting lambda very large, I can more or less invert the operator with a formula, and everything which is not exactly this formula is going to be an error term, which I would treat as an error term, okay? Okay, so next. Okay, next, let me try to devise a scheme which is going to kind of possibly do what I did with Nash, with the Nash scheme for the Euler equation. Okay, so I have my starting tripole, which is given by this guy. Okay, now I want to produce VQ plus 1. And how do I want to produce VQ plus 1? So abstractly, the way I want to produce VQ plus 1 is I want to put a perturbation, which is going to look roughly like this. So there will be some master function, big W, which I will try to cook up. And you have to think of this master function, big W, like in the Nash iteration, it's telling you, I have to take cosines of something, sine of something, multiplied by some other function, which actually is going to depend on the previous iterate in certain particular way, okay? So I want ideally to produce something which depends on VQ. So let me actually put X and T. And then I have the part in which I have the frequency to actually stick in which I have maybe lots of oscillation, okay? And this is another variable, and it's going to look like that. Okay, so ideally I would like actually to make a perturbation or devise a perturbation of this kind. Oh, yeah, sorry, of course, yes, sorry. So that's the danger of not looking at the notes. Thank you. Thank you very much. Of course, it's also depending on this. we will actually learn it still depends only on 2 of the 3 variables, because it doesn't, so this guy will actually not enter. It will play no role. But at the moment, at this level of generality, we are not yet going to discover this. So it will really depend on VQ, on this R circle Q, and then that will be the fast variables. Okay, now what am I hoping to do here? Okay, so let's think that this function W of x and t, okay, so this function W of, say, VQ or like something like VR, and then let me put it here, psi and tau, okay? Looks like something of the following type. So I expand in Fourier series in psi and tau, and it looks like something like the sum over k. Actually, let me even ignore about tau. Yeah, okay, it has tau has to be there. So something like, you know, e to the k dot psi. There has to be some numbers over here for this guy too. Let me call it whatever. You know what? It doesn't matter actually. Let me make only a Fourier expansion in this. So, and it's going to be some function a, k, which depends on v, r, and tau. Something like this. What am I hoping to do? Okay, so when I compute dt of VQ plus 1, right, I get dt of VQ plus a term which has a lambda. I'm not putting the Q plus 1 over here. A term which has a lambda, and then I will have d tau of W. Okay? So when I actually compute the divergence of VQ plus 1 tensor VQ plus 1, okay, oh, and then there are other terms. With no lambda though, order 1 in lambda, okay? When I compute the divergence of VQ plus 1 tensor VQ plus 1, I will have something like, you know, VQ, okay. So I will have lambda divergence psi of W tensor W, right? Then I will have, okay, so I have, of course, divergence of VQ tensor Q first. Okay, I will have lambda divergence psi of W tensor W. Then I will have VQ dot grad psi of W, and there's a lambda in front. Okay, so these are the ones with the lambda. Okay, then I have other terms. I have this one, for instance, W dot grad VQ. Okay, and let me just put it over here because it's important. I have a term that I want to isolate, and the term that I want to isolate is that I will have the sum of, well, okay, so let me actually not do anything over here. So let me just say that we have, when the derivatives are following, are not falling on this guy, but they are falling on that guy, okay? So order 1 terms in lambda. Okay, and then I have something for the pressure too. So Okay, that I don't want to write. So I have something for the pressure too. So I want to compute the same thing for the pressure, but you will see the pressure does not have no linearities, so gradient of PQ plus 1 is going to be gradient of PQ. Then, there is a lambda times gradient psi of the big function P, and then there are O1 terms. Okay, so now let me put everything together. So let me compute dt of VQ plus 1 plus VQ plus 1, so plus divergence of VQ plus 1 tensor VQ plus 1 plus gradient of PQ plus 1. And so there's going to be one thing which is going to be this. Then there is lambda times this guy. Okay, and then there are terms which are order 1. Okay, I wrote one of them, but of course there are others, and there are others which come from, say, differentiating the nonlinearity when I multiply VQ times, when I take W tensor W, but instead of like differentiating on the fast exponentials, I'm differentiating in there. Okay? So now it's time actually to write them a little bit better. So they're going to look like this in my Fourier expansion. Okay, so there is this it's going to be W dot grad VQ. Okay, and now let me write what are the other guys. So the other guys, if I write the Fourier expansion, they are going to look like this. So there's going to be the sum over K and J, and then I'm going to have something like e to the I lambda K minus J dot psi. And then I'm going to have, let me write it in this way. So AK, and this is where actually the divergence falls. So I have the divergence, and then I'm going to have AK tensor AJ. Right. That's it. And one thing which is maybe slightly bothering is that this guy does not look symmetric. It's not a symmetric matrix, but because I'm summing over K and J, when K and J are equal, I get actually something symmetric, AK tensor AK. And when J and K are not equal, I get, both of them. So I get AK tensor AJ plus AJ tensor AK. Okay, so this is the thing in all full glory. Okay, but now this guy I know is R circle Q, right? Divergence of R circle Q. Okay, and let me put it, okay, let me wait on where to put this guy. Okay, so what is my hope? So my hope for the moment, so this looks pretty messy, but my hope for the moment, let me give a name. Let me call this guy, whatever. Okay, so what is my hope now? My hope is to define R circle Q plus 1 to be the inverse of the divergence for the tensors of this whatever. And make lambda very large so that that one becomes small. And let me analyze if that is at all possible, okay? So now, one good thing is that when you have a fast oscillating term, e to the I lambda, times something which is slow, we actually hope of gaining 1 over lambda on that term. And so that will be small, okay? So if you're applying that idea to this part, you see that I'm already multiplying by lambda, and the best hope I have, which is not even clear it's really correct in that case, is to gain a 1 over lambda. And the gain of 1 over lambda will not do anything. So how am I going actually to make this, to pull this off? Well, W is me to choose, right? So I will want to choose W so that this guy is exactly equal to 0. And I will not, okay, spoiler alert, I will not be able to do it. And we were actually stuck for several years of thinking because we were not able to do that equal to 0. So we will be a little bit modest. Instead of making it equal to 0, we want to make it small enough. And why we will want to make it small enough? Because we still hope of gaining a 1 over lambda over here. So I don't really have to make it identically equal to 0. I need to make it small, okay? But for the moment, let's think that I want to make it equal to 0. And you see that if I want to make equal to 0, I got actually something very nice. I got the PDE in the fast variables. And so something that hopefully I can solve, okay? Very well, so this looks very nice. Why it looks very nice? Because it's exactly of the form we like. So W is a bunch of exponentials times AKs. Of course, you should tell me like, oh, okay, wait a second. There's one element in this Taylor expansion which I'm not going to have as a fast exponential. So I'd better be that K is different from 0, right? I mean, I don't want the constant term in here. Because if I have the constant term, I put the lambda over here, I'm not gaining anything, okay? So I avoid the constant term. I will only put oscillations. So this is going to be very nice. And you, I mean, Hyunju and Vikram, and I probably even La'szlo called it the Nash error term. And the reason why we call it the Nash error term is because it looks formally like exactly the error term which gave 1 over 3 in the Nash iteration, if you think about it, okay? It has one more derivative in the previous guy, okay? Actually, no, because I'm going to invert the operator. So I'm going to gain a -1 derivative. So it has one derivative in VQ, but then I invert the operator. So it's of order 0 in VQ, which is kind of, yeah, that would be even too good. No, let's say like it has the derivative in here, but then it has the inverse operator that I actually hope to be able to hit on this guy, okay? So it should be smaller. It should kind of go like 1 over lambda. Okay, these guys also look good, sort of, because there is the case in which K is equal to J. And when K is equal to J, this guy, of course, does not have a fast oscillating term. Okay, so let me split it into 2 pieces. So K different than J, and this is going to be called the oscillation error. So this is called the Nash error, and this is called the oscillation error. And like every mathematical term, which people gave at the beginning, it's a misnomer because what the fuck does it mean? Everything is an oscillation error. Everything is a fast oscillation times something. So I don't know why we called it actually the oscillation error. It's a wrong name. I don't know if La'szlo is not around, I could ask him. We call this oscillation error, but it's actually silly. Everybody is an oscillation error, so like it's a silly name. But okay, I mean, we selected and now it's stuck and now it's in the literature as oscillation error. But if you look at it like with some logic, it's like, okay, well, this one is also an oscillation error, right? I mean, it's a fast exponential times something which is going slowly. So what's the difference? Well, okay, now there's something missing. And what is the something missing? So the something missing, of course, is this term. So let me cancel the whatever over here, and let me actually add the final term. Okay? This does not average to 0. But it's actually exactly what I want. It doesn't average to 0, but not even this guy averages to 0, right? So let me put them together. Because that is the upshot of the consideration. Oh, the divergence is out. That's important. Why am I happy of having that term? Well, because I can engineer these guys so that they're equal to them, okay? These AKs, they depend on R circle Q. Exactly. So that is the famous geometric lemma. So now the famous geometric lemma is I'm going to actually find something in such a way that the sum of these AK tensor AK gives me that particular tensor. And you should immediately recognize that it's impossible. It's impossible because this guy is positive semi-definite, and this guy is trace-free. So have you ever seen a positive semi-definite matrix which is equal to a trace-free matrix? There's only one case, 0. And there's nothing else, okay? But we had that degree of freedom that we can add something, right? For instance, something depending on time is completely free because it does not depend on that. So here I want to actually add a function which depends on time. Now I can do it, okay? Now, when can I do it? Well, not always, right? I mean, I couldn't do it if f was 0. I can't do it if f is not large enough. But I can certainly do it only with a bound from below from f, okay? So remember this. So this has to be chosen in such a way that it's bigger than this guy. Then some constant times this guy. Remember this. This is going to be very important. In 10 minutes. Okay, so now we got a specification for this function w. So we got what we want from them, right? So actually, let me just observe the following. What is this AK tensor AK? It's just the average on the fast variables, on the variables which are like psi and tau, of my W tensor W, okay? So the way you actually get the 0 term in the Fourier series is by averaging the function. So here's what I want from my W. So I want to be solving this. Sorry? Yes. Or multiplied by the identity. Yes, sorry. It better be a matrix, right? Otherwise, what am I summing to? Yes. No, because I will want this somehow time by time. Well, certainly, because it has to be bigger or equal than that guy, right? Yes. Yeah. But I can change it. I mean, I want to be able to change it with time, okay? Not simply, I want to be able to change it with time. It will be one of the crucial points somehow. Okay, so now I got somehow my specifications for the master function. So specifications for the master function W. Okay, so I have the d tau W plus V dot grad psi W plus NP. Divergence psi W tensor W plus grad psi P is equal to 0. Okay, that's one specification. W should be periodic in psi and tau. Okay? Actually, it should really be periodic in psi. It doesn't need to be periodic in tau. But I will stick lambda very large inside my tau. And I want uniform bounds. So it should be a bounded function in tau, with bounded derivatives in tau, with bounded everything. And for lack of a good candidate of functions which do that, if they are periodic in tau, they're actually going to satisfy that assumption. Okay? But it doesn't have to be periodic in tau. If you find uniform bounds, it's fine. So let's say W periodic in psi with uniform bounds in psi and tau. If it is periodic, if it is a periodic also in tau, instead of saying uniform bounds, I can just say smooth. Okay, so it has to be smooth in psi with uniform bounds in tau. And then the final specification, right? So the average of W tensor W in psi has to be equal to R, to minus R, circle, plus the additional function that I'm going to give, F. So for the moment, let me just say F, it will be up to me to choose. And so let me just call this guy big R. And now I have something which is positive definite. I will furnish your function F, and I will be able to hopefully solve this. Okay, so here is something that you will sorry?
I mean, since W plus W, this is not test-free, of course, but if I demand that W plus W, test-free part is equal to minus
R circle, then you swipe everything in the pressure. Yes.
It's equivalent.
You could do that, yes. Not completely equivalent, meaning that then I actually have to go and compute the pressure with a different formula.
Sure.
But yeah, you could do that, yes. I could say that. That's a pretty good point. So here I was just exploiting the degree of freedom of adding a function of time, but nobody's telling me that I should do that. I mean, I can actually swipe everything that I put on the identity in the pressure, and it's a pretty good freedom to have. Yes, I could have done it that way. Yeah, but I will still want to add a function f of time anyway, and that is to adjust the energy. Okay? So I told you you can't do it. What is actually at odds with each other is solving this and getting smooth periodic in psi with uniform bounds in tau. The two things are at odds. But let's assume we can do it. So if we can do it, we can devise a mechanism which gives me VQ plus 1 from VQ, and it solves now the Euler equation with a much smaller error. Okay? Because I will get a 1 over lambda over here and a 1 over lambda over here. And as long as I'm not willing to discuss any better convergence, just C0, I can choose lambda as big as I want, just depending on whatever you gave me at the previous step. I don't need to actually even bother about how. If you gave me something smooth, it's varying slowly compared to the lambda which I will use. So why was the energy now, for me, free to choose? And that's the next computation I want to do. Let's compute the energy, okay? So there's going to be something like this, VQ plus 1 squared.
Sorry to
Yes.
Then you were saying that you might not get a W periodic and with these uniform bounds. Is that because of the transport structure of the equation?
Yep, we're going to see that. So I don't think I'm going to finish this today. So what will actually happen is that on Thursday, I will finish the C0 part and then I will start discussing the C0 alpha, which means actually that getting to the actual conjecture of Onsager will be faster. But okay, I think it's actually good that I kind of, you got a lot of information from the other speakers. It's actually good that I go slow and kind of review the start of everything because it gives you some sort of philosophy on how we actually approach things. Yes, it's correct. So we will be able to solve the stationary guy, but not the one in which there's also this kind of evolution. And so we will have to settle for something which solves this with an error. Exactly, and it's due to this part. But let me get to the energy. So now, what is this guy going to be, right? So this guy is going to look like this. Oh, yes, sorry. I mean, W where I insert, so here I'm going to insert VQ of xt, RQ of xt, and then lambda x, lambda t, okay, in that sense, yes. And the same over here, thank you. So how does this guy look like? Okay, so this guy looks like, in the Fourier expansion, functions which are actually going slowly times very fast sines and cosines. It averages to 0, right? I mean, it's like you integrate by parts and you get the 1 over lambda. So this term actually looks like a 1 over lambda. Now expand the Fourier in the fast variables of this guy. What it happens something like this, right? I mean, you will get all the scalar products of these people. You will get ak.aj, which is the trace of the vector tensor the vector, right? So good remark over here is that this guy is the trace of W tensor W. And we know what W tensor W is, right? So it's this guy plus that guy, okay? So these ones also will have very fast oscillating terms. So there's going to be a 1 over lambda. And then there's going to be a trace, the trace of this. And, you know, the trace of AK tensor AK, but, or if you want, the trace of this in Xi. But this was defined to be minus R circle plus F. R circle is trace free, so it's actually F. So you're just going to have this formula. So you now see why I didn't want to actually touch with another function which has the trace, which goes into the pressure. I just want to argue that with this system, the previous energy that you had, I can correct whichever way I want, as long as I stay below a certain inequality. So remember when we were kind of doing this Nash construction, I always wanted to be not too close to, well, I mean, this function f of q for me is kind of free. I can devise at each time how much energy I'm actually feeding into the system, as long as I'm free to add more energy. So I can use this freedom to actually make my energy along the subsequence to converge to the E of t that you gave me. So that's actually the freedom that we explored. That's why the total kinetic energy actually ended up to be for us to choose. Okay? Okay, very good. So now we got all of this. We want to actually solve this problem here. And let us start with with the toy problem. So as one of you already anticipated, the real trouble is in transporting this guy. See, one way I could understand to solve the problem, so maybe let me actually do it this other way. So maybe we understand this immediately, okay? So one way I can construct my solution is first of all to look at a stationary guy. Oh, maybe this was important. There's one equation missing, and that is because we didn't discuss the divergence-free condition. I should have done that. I mean, when you actually hit with the divergence-free condition, you're going to have divergence of VQ plus divergence of W. And when you actually hit divergence of W, there's a fast, which is going to give me the condition lambda times divergence psi of W. So I want that to be equal to 0. So I should have added that equation. And then I have an error, right? I mean, because I will not know, even if the divergence of psi of W is equal to 0, that I don't get some divergence when I actually differentiate the slow variables. But it's the same thing as before. I have a slow variable times a fast oscillating term. And then to correct for the fact that I'm not divergence free, I can solve the divergence to the -1 operator, okay? And that will get a 1 over lambda. So in actuality, my scheme is not really VQ plus big W, and that's it. I will need to add a corrector over here to make things even more complicated. This is what we call little wc. I will add a corrector to account for the fact that I will not be able to solve the divergence-free condition. So in all this mess, there will be other errors in which the corrector appears. But the corrector is already small in the actual norm without having to take advantage of the oscillation. It's 1 over lambda. So when I'm going to actually apply the operator R, I don't even actually need the oscillations. It will just be small in the correct norms. Same when I'm actually accounting for the kinetic energy. So I have this one over here too. Okay, so let me call a particular guy like this the stationary solution. Okay, and I will show you some. There's a bazillion of them. There's really many that actually do this job. So they are kind of, you see, I have an object over here which is a matrix, right? It's a single matrix. So I'm looking for a finite dimensional family or manifold of solution of the Euler equation, of the stationary Euler equation, which is parameterized by this R, by this symmetric matrix. So the dimension is going to be n times n plus 1 divided by 2. So I have this manifold of solution, which should vary smoothly with R. So it's really a manifold parameterized with R, which is solving the Euler equation and which is solving this algebraic condition. Okay, and there's many. And so this W stationary is a function of R, psi, and tau. Okay. Now, it doesn't solve the transport equation though, right? But maybe I can simply solve it in the following way. So because I'm not yet using the time, let me really try to solve dTW. Now it's not stationary, so this is going to depend on R, V this time, psi and tau. plus v dot grad w of r, v, psi, and tau equals 0, with w at time 0 equal to the stationary guy. Psi. Oh, sorry. This one, of course, is time independent too. Sorry. And it's silly, right? It's silly because this one is just a constant vector. So it's really just a transport equation. I'm just simply transporting my guy around. So if I go back to my ansatz for my function w will look in Fourier expansion like this. So it's going to be sum k is going to be different than 0. Then I'm going to have a k of r and v. Okay, and then I'm going to have some e to the I k dot psi, and then I have to transport that guy, right? So it's going to be something like psi minus v t tau. Okay, I even got my explicit solution. Now, what's wrong with this, though? Let me rewrite it in this way. Okay? So this is really the thing which is multiplying the Fourier coefficient. When I substitute lambda tau, I get ak of r and v, which is slowly varying, but then I have e to the minus I k lambda v tau, v dot tau. This one is not slowly varying. It's actually oscillating very fast. And all the point in my analysis was that I had something slowly varying multiplied by something fast oscillating. And this does not satisfy it. So I will need to do something different, and that is actually what I will start in my lecture on Thursday. So I will start from this point. So the something different that we will do, for instance, has a flavor of the following type. Like, discretize the set of possible v's, for instance. Just, all of the set of the possible v's. So then instead of exactly put a v over there, I put an additional summation and I put the discrete v's. And by using a partition of unity, I only try to use the v's which are very close to the one which I'm actually given. So in other words, I'm trying to actually get the dependence on v as much as possible outside of that fast oscillation and get it back to something which is slow. So I can approximate my v by, finitely many on a fine grid. Of course, I need the grid to be sufficiently fine because otherwise my approximation is not good. But that gives me an extra parameter. And that gives me my extra parameter, which you remember I wanted to play against lambda. So there's an extra parameter, which is, for instance, one approximation of my v with constant states. And with that extra parameter, I can try to kind of still get something small. So in the error, instead of having lambda and then dividing by lambda, I will actually have this extra parameter, we call it mu, and then I will divide by lambda. But mu is for us to choose. So we will get errors which depends by 1 over mu and errors which depends by mu divided by lambda. Then you optimize and you can still do the game.
You need cutoff to be steep.
Yes, that's the 1 over mu. That's the mu error. Yes. If I'm trying to make with a partition of unity, I will need the cutoff to be steep. Another method to do this is just to say, like, okay, let us not look at it as a W which is depending on time and space. Let us just do the stationary W. And then I will simply transport my stationary W along the flow. You saw that, okay? For a short time, it's somewhat well-behaved. For a long time, it's not going to be well-behaved. But for a short time, it's going to be well-behaved. Okay, then I will try to cut off in time. And this gives actually much better estimates. But it's somehow a very similar idea. So I can't exactly solve what I want to solve, and I will try to actually find an approximation to that. So instead of having that term to be identically equal to 0, it will feed me an additional error term. But you see that it was very delicate because we had one error term, which was already obstructing us to get actually to 1 over 3. So if this additional error term is going to be kind of something that we have to accommodate, which is somewhat of a similar value as the other one, we have to balance them, and we're actually falling from the 1 over 3 by some quantity. So the only way to really get to the Onsager conjecture is to get error terms which are way smaller than the Nash error term when we actually do this second parameter. So it's as if the dependence on the second parameter, rather than being a power, should be logarithmic in such a way that, you know, I'm off compared to the previous estimate, but just a very tiny bit. Okay, so my time is up. So let me stop over here.
Questions or comments?
Just a clarification. So the toy version, right? I think in the actual one, it's the Q that we are solving for. The W that we're defining there.
Yeah, I will, no, this is really an actual solution. So the point is I will substitute to V, VQ of X and T, and then to R, RQ of X and T. So it's not really a toy because, you know, at the level at which I'm thinking, the variables R and V are like as if they are frozen because, you know, it's a little bit like we did actually in the second lecture when we were doing with the Eichmann equation. So at first approximation, I just told you like, okay, I am actually at such a scale which is small that the gradient of V is just for my reasons completely constant. Now, the only point is you really have to understand in which sense it's really almost constant, right? I mean, because if it gets multiplied, I mean, as long as it's multiplying something fast oscillating or it's adding, I mean, the fast oscillation added to it, it's all fine. But if it's appearing in the oscillation itself, then of course it's not fine anymore. It's true that it's slowly varying, but it gets multiplied by the thing which is fast varying. And so I'm computing the gradient, like, you know, the second derivative, for instance, in the case of the Eichmann equation. So no, it's not a toy model. It's really what you want to solve, only you have to pay attention to why it is legitimate to assume that this guy is a constant. It's a constant, or like, you know, it's approximately constant as long as it enters in the formula in a certain specific way. If it enters into the formula in a way which is not that specific way, but in another way, it could actually lead to a wrong idea, to a wrong ansatz. But the master equations are really those. There's, you know, V now over there is not a function of X and T. It's really like a frozen constant. That's what I want to solve. Like, you see, what I was missing was really here, right? I mean, W, smooth, periodic in psi with uniform bounds in tau. I'm missing that. The reason why I'm missing that is because when I differentiate, so this is okay, it's smooth, periodic in psi. But when I differentiate, I get gradient of V times tau, and that is not bounded in tau, right? I mean, as tau becomes very large, that becomes very large. Of course, you could say it's periodic in tau. Yeah, yes and no, right? It's periodic in tau if V, for instance, is an integer or a rational number, but otherwise it's not periodic in tau. So that's where, like, you know, it's not a legitimate solution of the master functions because you're not abiding to this specification over here. That is the failure.
Can you say a few more words about this choice of f of t, that function you're adding? I guess it cannot be like 0, then you are not adding.
It has to be bigger than, I think I lost that. Yes, in such a way that you are in the region where you can kind of, use the geometric lemma. You see, the geometric lemma is going to look exactly like the geometric lemma of Nash, essentially, right? I mean, I want somehow sum of AK tensor AK to be equal to a symmetric matrix. It's literally the same geometric lemma. I don't even need to actually make a new proof, okay? If it has that shape, it's a tiny difference somehow in some of the applications. And then, of course, I need to be in the space of positive definite matrix. So I will need to add at least as much as the size of R circle Q, and then possibly stay a little bit away from it. I don't know, maybe a constant away from it, because then I want sort of uniform estimate. As you remember, like, we want it to be somehow on this circle, which is maybe, I don't know, around the identity, for instance. But there's one thing which is pretty good over here. You see, Nash had this annoying problem that I needed to add one step after the other. So if I add actually many oscillatory terms, it would kill me. It would kill my estimate. Here I don't care, because actually I'm adding all of them all together. Because the Euler equation have many more solutions. There are these manifold of solutions that do that. So if you're looking for a solution of Nash, which does this, it will not be possible, right? I mean, it will be possible only for some special choices of R. And then instead of doing it in a single shot, you will have to do multiple iterations before closing. And then your Hölder convergence is deteriorating. But here we don't have that problem. So at least that situation is lucky over here. So it pushes us immediately to this 1/3 regime, if you're able to control the other terms. Zero. Okay, so I'm sweeping under the rug how you actually make the very first time you get close to it. You can use the same ideas over here. So you will be able to, you will actually start with the stationary situation even, right? I mean, because V is equal to 0. So you will start with that. So because, of course, you want to produce, first of all, some starting point. And yes, the starting point could be simply the triple 0, 0, 0. It doesn't have necessarily to be. So you can choose a starting point which has kinetic energy, which is smaller than the kinetic energy you started with, okay? And then you can start perturbing that. I mean, kinetic energy plus error has to be smaller than the kinetic energy you started with, because you can only add, I mean, you need to add as much kinetic energy as the error you're given. So you can make a statement like, if the starting R circle 0 plus the kinetic energy is less or equal than the kinetic energy that you're given, I mean, strictly less, then you can actually start from that state and perturb to a solution which has the kinetic energy that you decided. So I'm not actually trying to match the initial data. If you want to match the initial data, there's some additional headache that you have to think about. For instance, you will not be able to match any initial data with an energy which is going down, because there's a theorem that tells you that as long as there is, as long as there is a smooth dissipative solution with a certain smooth initial data, any dissipative weak solution has to coincide with it. It's called weak strong uniqueness. So you will not be able to match an initial data which is smooth without increasing actually the kinetic energy immediately, right? By keeping the kinetic energy going down. That you will not be able to do. You will be able to match initial data which you actually construct with some care. Then you will be able to do it. Modulus of E squared of xt, yes.
So in the earlier scheme, you were not able to, like when you did for the Iconon kind of version, you were not able to attain this arbitrary E. Here in a C0 scheme, here you're attaining an arbitrary E. So, I mean,
Now, what would be the E over there in the Iconon equation?
So there you just operate where it was 1 for some time and then 0.
Yeah, no, but that is part of the equation. Huh? That is part of the equation. So the 1 of the Iconal equation is not the same as the E of t over here. Not really.
But what I was asking is that is there no connection between, so when we smooth them, of course the derivative of t would go on b and compute those two.
Yes.
But in general, is there absolutely no connection between how smooth the v is and the e that you're able to attain? Because here you're saying you can attain as many as you want.
Yes. It's more kind of the other way around.
Okay.
Of course, I cannot attain E's which are less smooth than what you're asking me about the smoothness of V. But you can attain E which are very smooth. Yes. Yes. Well, of course, if you want to show that the thing is not conservative, another way to do it is just to say, well, I can match the initial data equal to 0. And then I will make the energy increase. You can try to match initial data, even smooth ones, if you are willing to make the energy increase from the beginning. That you can do. What you cannot do is to prescribe an energy profile which is going down and the smooth, or stays constant, and the smooth initial data. And the obstruction is certainly going to be the weak strong uniqueness. But if you're willing to say, like, okay, I try to match some initial data, but I will have the energy going up. Okay, that should be possible. I mean, I don't know if somebody has written it down actually, but certainly that is what is happening, for instance, with the 0, with the compactly supported chi. But yeah, I would imagine you should be able to do it. And maybe there are even results of that. Yeah. Well, I know there are results of that in the formulation of, I mean, in the L infinity formulation. I mean, the results of Wiedemann, those were the ones which are quoted. Yes. Yeah, I'm not saying, I mean, this is how you should do it. I'm not saying that, that it's not, but it's written somewhere by somebody. Okay, I don't know a reference for that. For the C0 case, I know references for that for the L2. And that is Wiedemann. Fair enough. I mean, the paper is cited something like 700 times, so it's like it's something which is missing among the references which use the method. I'm pretty sure there are some.